Tylko teraz tutaj coś...
Z tej strony jest pokryte.
To? Tak właśnie ja myślę. Ciekawe. Nie wiem, właśnie z tym stawiają coś.
Tu jest. Tam musi być coś. A, to jest pokrętło. Czyli to pokrętło zużyte.
Good afternoon. It's my pleasure to announce the talk by Borys Kuca, who is now from the Jagiellonian University. And the title is Arithmetic Patterns in Large Sets. Please.
Thank you. Thank you very much for introducing me, for inviting me here, and for bestowing this prize for me. It's an honor and pleasure to be here. So today I'll talk about a very general question concerning finding patterns of arithmetic natures in large sets. And more specifically, the kind of question that will motivate the content of today's talk is the following. What patterns or what configurations can be found in large sets, where we can look at sets of natural numbers, integers, finite fields, reals, primes. Now better? Better or not better? Shall I speak louder? Okay. So I'll try to speak louder. So this is the question that will motivate the content of today's talk. Let me first explain what I mean by patterns, because this is obviously a very general term. So for me, patterns would be the following things. The simplest pattern that you can think of are arithmetic progressions. So for instance, a three-term arithmetic progression is a triple of points of the form x, x plus n, x plus 2n. Instead, we can look at so-called Schur triples, which are things of the form x, n, x plus n. And whereas our three-term arithmetic progressions equivalently are solutions to the equation x plus y equal 2z, Schur triples are solutions to the equation x plus y equals z. Both of these patterns are linear in the sense that x and n, all the expressions there are linear in the parameters x and n. But we can also look at patterns which are, say, polynomial in these parameters. So for instance, we can search for polynomial progressions like progressions of the form x, x plus n, x plus n squared. Or we can look at patterns which are completely non-arithmetic in nature, in the sense that they don't come from functions which can be defined in terms of the four arithmetic operations. So we can also look at patterns, for instance, which involve things like log n or so-called fractional powers of n. And the last of the patterns here is an example of such a configuration. And moreover, we want our patterns to be non-degenerate, in the sense that we want all the terms to be distinct. So for instance, for a three-term arithmetic progression, we want all these three numbers to be different, which is equivalent to saying that the difference n is not zero, right? Otherwise, it's pretty easy usually to find degenerate patterns. So I'll assume throughout that all the patterns that I'm speaking of have this non-degeneracy assumption. Now, perhaps the most classical result in this direction is a celebrated theorem of Semeredi from almost 50 years ago, which concerns the presence of arithmetic progressions in large sets of natural numbers. And the theorem says that each dense subset of natural numbers contains an arithmetic progression of arbitrary length. Where for me, a subset of natural numbers is dense if it has positive upper density, which means that the following limb sub here is positive. So intuitively, this means that this set contains a positive proportion of all the natural numbers. And sets that are not dense, I'll just call them sparse. So for instance, the set of odd numbers is dense with density 1 over 2, because roughly speaking, every other natural number is odd. Whereas the set of primes would be sparse, because the density of primes, as we know from the prime number theorem, grows like 1 over log n. So these are two examples that will maybe give some context behind these definitions. So we have this theorem of Semeredi, and let me maybe state very quickly that this theorem would fail if we replaced arithmetic progressions with Schur triples. And we have a very simple counterexample for this. If we take the set of odd numbers, then they will not contain a Schur triple, for very simple modular reasons. If x and n are odd, then x plus n will have to be even. So it's not possible to find a configuration like this inside the set of odd numbers. And these two examples and the contrast between arithmetic progressions and Schur triples illustrates a more general heuristic. That is, we should expect dense subset of natural numbers to contain a pattern of a certain form unless there is an immediate reason for the pattern not to appear. For Schur triples, there was an immediate reason, an immediate modular obstruction that allowed us to construct a dense subset of natural numbers without such a configuration, whereas no such obstruction exists for three-term or longer-term arithmetic progressions, and indeed, dense subset of natural numbers do contain arbitrarily long arithmetic progressions. So, Semeredi theorem is a very famous result and quite a celebrated one. It's often mentioned as an example of deep mathematics or good mathematics. As I was preparing my PhD thesis, I even found this article in some philosophical journal, which used the Semeredi theorem to discuss what one can conceive of as deep mathematics. Also, Terence Tao has an expository note somewhere where he uses the Semeredi theorem to discuss what to him is good mathematics. So the Semeredi theorem has often been used as an example for profoundness in mathematics. And why is that so? There are several overlapping and non-overlapping reasons for this. Perhaps the simplest one is that there are close to 15 different proofs of this theorem. I don't know the exact number, and this changes because from time to time someone comes up with a new proof. And of course, sometimes it's hard to say whether two proofs are different enough or not. But the important thing is that these proofs rely on insights from quite a broad array of mathematical areas. Combinatorics, number theory, and also ergodic theory, harmonic analysis. Some of these proofs use some very deep things from Lie group theory, There are also proofs in terms of model theory. So there are different proofs using different mathematical areas. And at the same time, there are some deep underlying ideas that appear in most of these proofs. So even though the ways of framing these proofs are different, there are some similarities, some very fundamental underlying similarities between most of these proofs. Another reason why similarity theorem can be thought of as an example of deep mathematics is because its proofs introduce quite a few new techniques. And similarity theorem has also introduced quite a few new research directions. And indeed, there are plenty of interesting generalizations of this result, some of which I'll discuss in the later part of the talk. Perhaps one last measure of why this theorem can be considered interesting is because it has seen major contributions from a number of high-profile mathematicians. And this includes 4 Fields Medal winners and 2 winners of Abel Prize, all of whom have made some really, really fundamental contributions to the similarity theorem and surrounding areas, and introduced quite a few new techniques that have ever since inspired further mathematicians. So throughout this talk, instead of discussing my own results, which I think wouldn't be a good idea for the diverse audience that we have here, I'll rather discuss briefly the 3 main proofs of the similarity theorem, together with some of the research avenues that these proofs opened up. And at the end, I'll move to discuss the state of the art at the moment. So as I said, there are about 15 different proofs, but there are 3 proofs which have been truly groundbreaking. The first, that's of course the original one, which is similarity, which is based on graph theory. Then 2 years later came a proof by Furstenberg, which is based on ergodic theory. And about 25 years after the original proof, Tim Gowers gave yet another proof of similarity theorem, now based on free analysis and its manifold generalizations. So let's start with the similarity theorem, with the Semiramis proof of similarity theorem, and some of the new ideas that it introduced. So similarity introduced quite a few new tools in each proof, but perhaps the most interesting one was the so-called graph regularity lemma. This is a result which allows to decompose a graph into 3 pieces, where one piece is structured in some sense. I'm deliberately keeping this vague. Another one behaves very randomly and resembles essentially a random graph, a uniform one. And then there's some small error term in between. Now, this result has been used by Semiramis in order to prove the theorem, but since then, various refinements and generalizations of this regularity lemma have been used and constructed by other people in order to resolve many other problems in mathematics. So for instance, similar decomposition results can be found for functions. And so for instance, if we have a function which is bounded, takes complex values, let's say, and it's, let's say, defined on a cyclic group, then we can also decompose it in a similar way into 3 pieces, where the first piece is bounded in some sense. In this case, the bounded means that it's essentially a bounded degree trigonometric polynomial. Then we can also find a uniform piece, where uniform in this context would mean that it has uniform in the sense of Fourier analysis, so it would have no large Fourier coefficient. And then there will be some small error term in between. And these regularity lemmas have found great applications, as I already said, in similarity theorem and similarity type problems. So for instance, here's how we can use this last decomposition result in order to count the number of 3-term arithmetic progressions in subsets of Z0 and Z. This is essentially equivalent to proving that large subsets of this group contain 3-term arithmetic progressions. So if we want to do this, this would be the count that we would like to estimate. And we would split this count according to this decomposition, this regularity lemma, as this is called in literature. And then by various means, one can show that all terms that contain either the uniform or the small function can be discarded. And we're only left with the count in which the indicator function of our set A is replaced by the structured piece of the function. And for this, we can easily, or not so easily, but fairly easily, we can find a lower bound for this count by using the extra information that this structured function is structured in some useful sense to us. So these are the innovations of Semeredi. Let me now move on to the second important proof, which is one by Furstenberg. This proof was based on ergodic theory, and since this may not be very familiar to some of the people, let me start with some very basic definitions here. So in ergodic theory, the setup is like this. We have a probability space, by which we mean a set endowed with some probability measure, and with sigma algebra, so a collections of set subsets to which we can assign measure. And apart from that, we also have a measure preserving transformation. So a transformation of the space such that each set has the same measure as its pre-image. And this together we call a measure preserving dynamical systems. So what ergodic theory does is it studies the limiting behavior of averages of this form. So what we have here is we have some function f, we have some point x, and we study the average value of this function f along the orbit of the point x. Where by the orbit of the point x, I mean points x, tx, t squared x, t cubed x, etc. And in many cases in ergodic theory, under many natural assumptions, we can show that the limit of such an average is the integral of f over our space. And this is the content of so-called ergodic theorems. Another thing that is very much studied in ergodic theory is the concept of recurrence. So perhaps the most classical result in this direction is an early recurrence theorem by Poincaré, who showed that if we take a set which has positive measure, then for some time n, the following intersection will also have a positive measure. In other words, we can find a time n such that sufficiently many points of the set A return to the set A, so that this intersection has positive measure. Now, this was Poincaré, and this result is very easy to prove. It's essentially an application of the pigeonhole principle, but its extension due to Furstenberg is nothing short of spectacular. So what Furstenberg showed is that not only do we have a single recurrence like this, but in fact we have a multiple recurrence, meaning that for every natural number L, we can find some time n for which this intersection of L plus 1 sets also has positive measure. In other words, there exists some number n such that, and a large collection of points inside the set A such that they return to the set A not only at time n, but also at time 2n, 3n, etc. So this is one thing that Furstenberg proved in his proof of the Semeredi theorem. And then he also showed that this multiple recurrence theorem is equivalent to the combinatorial formulation of Semeredi. And in doing so, he showed that a lot of problems from active combinatorics can be rephrased in this language of ergodic theory, and one can apply the whole ergodic toolbox in order to show the existence of various patterns in dense subsets of natural numbers. Now, Furstenberg's approach has been extremely important because the methods that he introduced have been more robust than any other methods that we have in finding new patterns in subsets of natural numbers. In particular, about 20 years later, Bergelsson and Leibman proved the following polynomial extension of the Semeredi theorem. They showed that if we take any collection of polynomials with integer coefficients and with zero constant terms, then each dense subset of natural numbers will contain a polynomial progression of the following form. So in particular, to have something concrete, this shows that each dense subset of natural numbers will have 3 points of the following form. And the result is not true in general. So for instance, if we take polynomials which do not have zero constant terms, it may fail. And here's one simple example. The reason we have this configuration and it will not be contained in the set of multiples of 3. The reason why this is the case is because the polynomial n squared plus 1 is not divisible by 3, and hence we cannot find 2 points which are both multiples of 3 and which differ by a number of the form n squared plus 1. So again, we have an almost immediate reason why this pattern would not appear in dense subsets of natural numbers. However, proving a positive result here is an extremely difficult task that was only accomplished 20 years, almost 20 years after Furstenberg's or Semeredi's proofs. And by now, by the way, there is no full proof of this result that would avoid ergodic theory. The only proofs that we have are phrased and rely heavily on ergodic theorem methods. And let me, towards the end, discuss the last proof of the summarily theorem, the last of the important, of the three groundbreaking proofs of the summarily theorem, which is due to Gowers. The difference between this proof and the previous two proofs is that this proof gives explicit quantitative bounds for the size of finite subsets of natural numbers which do not contain arithmetic progressions. And this is because Gowers employed free analysis or some generalizations thereof in order to get a finitary quantitative result, which implies summarily theorem in particular. So what Gowers showed is that for each L, we can find some absolute constants such that for each sufficiently large number n, every subset of the first n natural numbers, which has at least that many terms, will contain an arithmetic progression of length L plus 1. And having proved this result, Gowers initiated more quantitative approaches to summarily theorem and towards finding other patterns in that sets of natural numbers. And so in particular, in the last few years, there has been an outbreak of activity in finding polynomial patterns in finite subsets of natural numbers. So for instance, a few years ago, Prendeville obtained bounds for subsets of natural numbers lacking arithmetic progressions with, say, square or cubic common differences. And a few years later, Pelouse and Prendeville proved bounds for subsets of numbers from 1 to n lacking this kind of polynomial configuration. And as I said, this field is very much more active. New bounds appear all the time. But perhaps the most spectacular refinement of Gowers' method came due to Green et al., who used Gowers' approach together with quite a few new ideas in order to prove their really spectacular result about arithmetic progressions in primes. So they proved that the set of primes contains arbitrarily long arithmetic progressions, and this result has been cited as one of the results that brought Tao a Fields Medal in 2006. And later on, this result has also been extended to polynomial progressions by Tao and Ziegler. So these were the three main proofs of summarily theorem, and as I tried to show, each of them introduced some new ideas and initiated new areas of study, new research directions. So all these things can be now combined into the following slide, where I'll try to give you some idea of where we are at the moment, what are the other research directions that are currently prevalent in this area of finding patterns in dense subsets of natural numbers. So there's a big line of research first, which is concerned with determining what other patterns can appear in dense subsets of natural numbers. And then this is qualitative, because for this we don't necessarily care about bounds. We just want to know that a pattern of a certain form is contained in dense subsets of natural numbers or other sets. There are various methods that one can employ here. The most successful ones, though, came from ergodic theory. And in order to prove that a certain pattern appears in dense subsets of natural numbers, the thing that one has to do first is to understand the limiting behavior of certain expressions that come out of ergodic theory and which are crucial in order to determine the existence of various patterns. So these expressions are called multiple ergodic averages, and in general they take a form like this. So now we have an average, but we average not over a single term, but over a product of terms, where each term is some function evaluated at some iterate of some transformation of the same point x. So here T1 through TL will just be some measure-preserving transformations on our space. They may be the same, they may be different when commuting, they may generate an important group. Each of these levels of generality introduces new challenges. But this is the basic object that we're trying to understand in ergodic theory in order to find new patterns. And A1 through AL are sequences in terms of which that appear in the patterns that we want to investigate. There's also the second line of research, which is more quantitative in spirit, which has been essentially initiated by Gowers, and which concerns itself with determining how big a subset of the first n natural numbers can be if it does not contain a certain pattern. Or equivalently, what's the threshold such that if the set passes the threshold, then it must contain a pattern of a certain form. And there's nothing special about the natural numbers from 1 to n. By the way, one can inquire about the same things in other spaces. So for instance, one can ask the same question in, let's say, cyclic groups, in vector spaces over finite fields, in more general finite commutative ring, but also in a more continuous context. So for instance, in subsets of R. And these methods usually use refinements of Fourier analysis plus a bit more number theoretical context, since one needs to get some quantities here. So this is where this field of finding patterns in large sets stays at the moment. I've presented several key groundbreaking results that appeared over the years. My work personally regards both of these questions. So some of my work, especially some of my recent work, concerns understanding the L2 limits of expressions of this form, especially where the sequences are polynomials and where the transformations commute with each other. But I have also worked a bit with the second question, namely with determining the size of sets which do not contain certain patterns. Although so far I've mostly worked not with the set of natural numbers from 1 to n, but rather with the cyclic group of n elements where n is some large prime number. Thank you very much.
Thank you very much. Are there any questions? Yes, please.
Thanks a lot for interesting lectures. A number of theorists like to ask the question about the primes. Of course, we have famous conjectures like Schünzel H conjecture or even simplest terms. Can these methods give us any hope of proving something like that?
So I don't know these conjectures very well, but these methods mostly concern.
No, I specified this to n squared plus 1, for instance, the polynomial pattern of primes. Is there any hope?
But so you would like to find
infinitely many primes of the shape n squared plus 1.
I don't think so.
I don't think so. Okay, so the other related question is about your thresholds things, because you have large sets on one side and say sparse as primes on the other. And then in the between there is a lot of space. Yeah. So for instance, concerning the regularity, lemma obscenity, can you spot the place or the set which will be the threshold for the size of the set?
So, okay, so regularity lemmas tend to be pretty ineffective in terms of the quantitative input that they give. So when one tries to get some quantitative statement, usually one tries to avoid as much as possible to get regularity lemmas, because there are some, let's say, negative results showing that the quantities and the quantitative dependencies that appear in the regularity lemma can be very bad. In terms of the, let's say, threshold between natural numbers and primes, most of the bounds that we have obtained so far lie somewhere in this threshold. So most of them would not tell you that the set of primes contains a certain pattern. There are some notable exceptions. So for instance, in the case of Roth theorem, which is the case of length 3 similarity theorem, recently there have been 2 new bounds that beat they beat the threshold that is required for primes. So for primes, we would need the density of the set among the first n natural numbers to grow like 1 over left n in order to guarantee the existence of patterns in primes. And they beat it recently first to 1 over log n to some power greater than 1, which already beats it. And then by different methods, there was a further refinement with much better bounds. But in general, the bounds that we get are not good enough in order to handle primes. So usually one has to deal with primes separately and use some other properties of primes, such as some kind of pseudo-randomness that the primes execute.
Thanks.
Any other questions? Yes, please.
So you mentioned this Bertelsen-Lyman theorem and Gauss theorem. So if the two theorems had a baby, what would it look like? Do you know?
If they had a baby, then, well, you would like to get bounds for things like
if you would like to, so have some polynomial pattern, then what would the threshold be? Do you have a decent expectation here?
So for instance, for this thing, for arithmetic progressions with higher degree differences, you expect the same threshold as for usual arithmetic progressions. And indeed, for arithmetic progressions where the differences are squares, cubes, or some other higher powers, the bounds of Prandtl is also the same form. The exponent little c is worse than in Gauss's bound, but at least the shape of the bound is similar. For this thing, the bounds are better actually than for arithmetic progressions. So you have something like n over log n to some small power. And in fact, some people surmise that for this you might get polynomial bounds, so bounds of the form n to 1 over minus c for some small constant c.
Okay, but is there like a completely general expectation?
Not really. So for polynomial progressions, okay, my expectations would be that if you give me much more general polynomial progressions, then maybe you would get many logs here to some small power. I would believe that this is the case. How many logs is enough, that I don't know. But essentially, the only things that we can handle for the moment are things that look like arithmetic progressions. I mean, to get bounds, or things where the polynomials have distinct degrees. And it turns out that the more algebraic relations there are between these terms, then the more complicated the whole analysis is, and presumably the worse bounds you get. And in particular, the tools that you would need to have in order to handle the polynomial progressions of more complicated form are the versions that we have at the moment are much worse than what we expect to have, and they give very bad bounds. So we will have to improve first some of the tools that we use, which they're called inverse theorems for Gauss norms, and only then could we hope to get much better bounds for in the general case of the polynomial similarity theorem.
Pass the microphone.
So the perfect slide, because I wanted to ask, was the dependence of the constant little c on L, the length of the arithmetic progression?
Yeah, good question. So this constant is actually given explicitly, something like 1 over 2 to the 2 to, okay, it's double or quadruple exponential in L. I don't remember which one, but it's explicit, it's very bad, very weird, but it's explicit, and that's more than we can hope for in any other.
Thanks.
Are there any other questions? Yes, I see a question there.
Excuse me, so is the version of the theorem if this state named it Poincaré recurrence theorem sufficient for some of these results? Because I've just checked that it isn't, I believe, really a Poincaré recurrence theorem in its full strength and full generality.
So I'm not sure if I understood the question, but in order to get, let's say, to prove similarity theorem, you need more than Poincaré recurrence. This is just a baby case that was proved many years ago, and it can be strengthened in various ways. But really, we need extensions of this theorem. So we need not just a single recurrence, so not just Tn, but we need multiple recurrence, so recurrence at various times.
Okay, thank you.
But yeah, like most of these things that I stated here can be strengthened in various ways. Right? I just stated the more accessible versions.
Okay, I think that the next questions we will already ask Borys, personally, I would like to thank you for this wonderful talk.
Co napisz do mnie, wiesz, jak to na przykład, ja planuję teraz
Oh, yeah. Now I got it. Okay. Yeah. Sorry for all of this mess. I need a. Can I use this microphone? Yeah, I want
Okay. Good afternoon. So it's my pleasure to introduce Guillermo Lorenzo, who will talk on imaging-informed patient-specific computational modeling of organ-confined prostate cancer.
Okay, thank you very much for this introduction, and I want to thank the organization for inviting me to present my work today. I will be providing an overview of my work on imaging-informed patient-specific computational modeling of organ-confined prostate cancer. And towards that end, I will start with an introduction on what is the prostate, what's prostate cancer, and how mathematical modeling can help us address big challenges in the clinical management of this disease. Then I will move on and present 3 different models that I have developed over the last years. The first 2 ones are going to be aimed at describing the mechanisms of prostate cancer growth, whereas the third one is going to aim at practically implementing this modeling pipeline with clinical data. And then at the end, I will move on and draw some conclusions. So let's get started. So the prostate is a small organ placed at the intersection of the urinary and reproductive systems of men. And its role is to produce secretions that have a very minor role in human reproduction and also keep the urinary tract clean. From a radiological point of view, we can divide the prostate in 2 main regions. The central gland, which is the blue part here, and the peripheral zone, which is the gray part over there. And despite the tiny size of this organ and its supporting role, it's the place where 2 major pathologies affecting aging may take place. The first one is benign prostatic hyperplasia, or BPH, which is a disease that consists of the enlargement of the central gland of the prostate over time, and that provokes problems with urination and ejaculation. So this is a disease that has a very high prevalence in men, and it increases over age. It can have different growth rates, and it can affect different parts of the central gland, but fortunately, it can be addressed with either surgery or specific drugs that reduce the volume of the prostate to facilitate urination. On the other hand, prostate cancer is a major health problem worldwide, with leading rates of incidence and death all over the world. Usually, prostate cancer is an adenocarcinoma. This means that it originates in the glands that produce the secretions within the prostate. It usually starts in the peripheral zone, remember, the outer part of the prostate, but it can also develop in the central gland, that is in the central part of the prostate. And as many other solid tumors, it has 4 key stages of development. In the first stage, prostate cancer is a proliferating mass of cells that grows in size until it is detectable using imaging techniques. That would be stage 2, where the tumor is still confined within the prostate. Then at a third stage, some of the tumor cells reach the boundary of the prostate and escape outside. And in the last stage, some of these cells start invading nearby structures like the seminal vesicles or the bladder. And during this stage, some cells may even enter the bloodstream and migrate to other parts of the body, developing what we know as metastases, which are secondary tumors all over the body, for instance, in the bones, the kidneys, or in the liver. So how are we managing this complicated disease? Well, this is an overview of what the clinical management of prostate cancer looks like, and I'm going to walk you over there. There are some ideas for the prevention of the disease, but the first cornerstone of managing prostate cancer consists of regular screening of men over 50 years of age. And it consists of a digital rectal exam and a blood test to measure a biomarker called prostate-specific antigen. If either of these 2 tests is positive for the suspicion of prostate cancer, then the patient is going to get imaged, usually a magnetic resonance imaging. And that imaging information is going to be used to do a biopsy, that is, to direct a needle to retrieve some samples of tissue from the prostate, which are assessed by histopathologists in order to determine the cellular architecture of the tissue samples and characterize them with a system called the Gleason score, which is a natural number growing from 2 to 10, where lower scores from 6 and down are considered lower risk prostate cancer, and the scores going from 7 up to 10 are considered higher risk prostate cancer. Taking together all this information from a prostate cancer patient, clinical guidelines recommend, clinical guidelines prescribe a risk group, so low risk, intermediate risk, and high risk. And associated to each risk group, we have different managing options, which can be summarized in either monitoring the patient with different monitoring exams, like imaging or blood tests, that's called active surveillance, or treating the patient right away. And for prostate cancer, that consists either on surgery or radiotherapy, and they can be also combined with hormonal treatments in order to boost therapeutic performance. After treatment and during surveillance, the patient is also followed up with PSA tests and medical imaging. So how is this strategy working right now? Well, first, good news. The majority of tumors are detected at low or intermediate risk. and less than 5% of tumors are metastatic at diagnosis. That means that the tumor is at a very early stage, usually at diagnosis. But paradoxically, the majority of tumors are treated right away, while then a lot of them could be candidates for active surveillance. So this is a very big problem in the clinical work, because it means that a lot of patients are overtreated. And this means that these patients can have can suffer from side effects from the treatment, for instance, problems with urination, with ejaculation, or even infection and inflammation, that can dramatically affect their quality of life without prolonging their life expectancy. And therefore, they would have been good candidates for monitoring the disease instead of treating it. But perhaps more importantly, other studies have looked at the under-treatment of patients, and the percentage is also quite significant. And this means that the current strategy is not characterizing the tumors well enough, and then the treatment that is prescribed on the patients is not correctly targeting the tumor so it can come back, and when it comes back, it's usually more malignant than the original tumor. So there is a lot of interest in refining the current strategy of managing prostate cancer in order to improve its personalization, because right now it doesn't go beyond defining a risk group and just looking at the set of treatments that are recommended for each risk group category. So in the clinical world, the solution to this problem has been precisely active surveillance. So let me just introduce a little bit more what this means. During active surveillance, patients with low risk or intermediate risk are followed with periodic PSA tests, so blood tests, and a magnetic resonance imaging in order to control the evolution of the disease. And once either the PSA tests and or the MRIs detect progression, that is progression towards higher risk disease, then another biopsy is prescribed. And if there is confirmation of a higher Gleason score, then the patient is removed from active surveillance and prescribed a treatment. But what's the problem with the current strategy of active surveillance? Well, the problem is that it's based on population-based protocols that only assess cancer. This means that we know that cancer has progressed the moment that we do our monitoring exam. And also, the frequency of the test is mandated by protocols that assume an average patient, and they recommend those frequencies for the tests based on that average patient. That means, but in reality, the patients may have very different growth rates, and that means that some patients that have very slow growth are over-tested, and they may abandon active surveillance because they want to get treated right away because of anxiety. And on the other hand, we have patients where the tests are very spaced apart, and the tumor progresses within the test, so it may be too late to get an effective treatment. So in order to address these limitations of active surveillance, here's where mathematical modeling, in my work in particular, enters. What I try to do is to build a patient-specific organ-scale computational technology to forecast prostate cancer growth in the context of active surveillance. So I want to move from a population-based protocol to a patient-specific technology that does not only assess tumor evolution, but also predicts it, such that we can take action before progression takes place. And at the core of this technology, I use mathematical models that describe the mechanisms of prostate cancer growth. So the main idea is summarized in this slide. I have my mathematical model, which I parameterize and initialize using MRI data and also clinical data such as PSA. Once the model is initialized and parameterized using longitudinal data from a patient, we can perform forecasting and obtain predictions of tumor growth that we can further validate with extra data in the future. So in order to do this, the first thing that needs to be developed is the mathematical model. And when I started working in this problem, I understood prostate cancer as a two-phase dynamic problem. And I used the phase field method in order to address it. So in the phase field method, you define a variable called the order parameter or the phase field that generally describes the healthy tissue and the tumor tissue. That is, the two coexistent phases. In my case, healthy tissue is phi equals 0, and the tumor is phi equals 1. In between them, you have a smooth interface. Then, when you apply the method, you try to minimize an energy functional that describes the governing dynamics of the system, and that yields this first PDE here, where the first two terms emanate from the energy in the interface, and the last two terms introduce biological properties that drive the evolution of the interface. In particular, I will highlight that this function f is a double wall potential that is necessary for the stable coexistence of the two phases. Regarding the two reactive terms, they represent nutrient-driven growth rate or growth term and an apoptotic term, which means a tumor cell death term. Then the nutrient is driven by a diffusion reaction equation where the reaction terms represent the nutrient supply, the nutrient consumption by the tumor, and then a natural decay that governs the consumption by healthy tissue, and then natural decay for other chemical reasons in the tissue. And then to make the model prostate specific, we wanted to include the biomarker PSA. What we did is we defined an ancillary variable called the tissue PSA, which is the PSA in blood produced per unit volume of prostatic tissue. And we can define the dynamics of this variable with another reaction diffusion PDE, where the reactive terms are the production of PSA by healthy tissue, by cancerous tissue, and then a natural decay. And to retrieve the serum PSA that is used in the clinic, we just need to integrate over the geometry of the prostate this little p or tissue PSA. To complete the model, we define typically boundary conditions for the phase field because during active surveillance, the tumor has to be growing inside of the organ. If it reaches outside, it automatically doesn't qualify for active surveillance. And then we define zero flux boundary conditions for the other two variables. Now, how can we make this model work with patient-specific data? Well, first of all, we're going to use a generalization of the finite element method known as isogeometric analysis. So if you're familiar with finite elements, the idea is that you want to approximate the variables of your model, for instance, the phase field, as a linear combination of some basis functions and some terms that depend on time. And the difference between finite elements and isogeometric analysis is that in finite elements, you use linear polynomials that are defined over each of the elements, whereas in IGA, or isogeometric analysis, we use functional bases that come from computer-assisted design, which are usually spline bases that are defined over more elements. So they are highly continuous all over the domain. And for example, that means that over this element here, we have 9 basis functions for this quadratic class 1 spline functional bases that are not only defined over the central element, but also on the nearby elements. And because of this higher continuity across elements, we have better numerical approximation properties. I will not delve more into the details of IGA, but if you're interested, I recommend you to check out the book on IGA of Professor Hughes, where you can find all the mathematical details and applications to different fields. Going back to our problem, we need to build a mesh for the patient's prostate. To do that, we're going to use a parametric mapping method. So to do that, we need first 2 ingredients. First, a volumetric definition using an spline basis like non-uniform rational B-spline to represent the volume of the thorax. And then we need a representation of the surface of the prostate, which we can draw on medical imaging from the patient. In particular, for this study, we use computerized tomography scans or CT scans from a patient that was provided by the Osteopathic Association. And what we do is we take the outer surface of the thorax and we deform it to map it on the surface of the prostate that we draw over the medical images. And after we have that mapping, we then adapt the internal volumetric parameterization to get our mesh of the prostate. Then regarding time integration, we use the generalized alpha method, which is a second-order NAS table, and it involves doing nonlinear iterations, which we solve using the Newton-Raphson method. And then we solve the ensuing linear systems using the generalized minimal residual method, or GMRS. So using the mathematical model and these numerical methods, we are playing with parameter values that we found over the literature. We arrive at an implementation of our model that was able to reproduce prostate cancer growth with shapes that match what was observed in the surgically removed prostates after surgery. Also, when we integrated the phase field and the serum PSA over the volume of the prostate, we got these exponential trends or quasi-exponential trends that match the observations of tumor volume and PSA over time for the patients in active surveillance. So we were happy that our model was reproducing qualitatively how the tumor grows, and we wanted to investigate more what other mechanisms would be needed to represent prostate cancer growth. And the first question that came up was, okay, so many patients have prostate cancer, but because of age, they can also have BPH. So is there any connection between both that may affect the way prostate cancer develops? And without knowing it, we entered in one of the major debates of the urology community, because up to now, it's not clear how these two diseases interact with each other. This is working here. how they interact with each other. But we found a collection of studies that were looking at what were the pathological features of tumors that grow in prostates of different sizes, that is, more or less affected by BPH. And we found out that tumors in larger prostates tend to have more favorable pathological features. This means that as the volume of the prostate increases, the probability of having a high-risk disease during biopsy, during surgery, is lower, and also the tumor volume is lower, and the probability of extra growth of the tumor outside of the prostate is also lower. So because of this, we wonder, well, perhaps what's happening is that mechanical stress generated by tumor growth and BPH are added together, and that restrains the tumor growth. And on the other side, it's also known that mechanical stress can slow down tumor dynamics. For instance, here I'm showing the results from Haulinger and colleagues, where they try to grow tumor spheroids in different gels with increasing rigidity. What they observed is that the final volume of the tumor spheroids was smaller and smaller as the rigidity increased, and also the velocity of growth was also slower. So we took these results and also recent developments in mechanically constrained tumor growth modeling, and we decided to extend our model. And to do that, we needed to define a mechanic problem and combine tumor growth with mechanics. So let me start with this last one. To combine tumor growth with mechanics, we use a mechanotransductive function, M of sigma, where sigma is the stress tensor. And from the stress tensor, we want two metrics, the von Mises stress and the hydrostatic stress. So the von Mises stress characterizes the distortion of tissue around the tumor, and the hydrostatic stress represents the natural stress state within the tumor, which is usually compressive. Nevertheless, because of the distortion around the tumor, there are some parts of the boundary of the tumor where the hydrostatic stress can be positive. But this is not facilitating tumor growth. Quite the contrary, because of the distortion, it's more difficult for the vascular tree in that part of the tissue to irrigate the tumor, and because of that, the tumor also slows down. So that's why we take the absolute value for the hydrostatic stress here. And as either these two stresses increase, the mechanotransductive function takes lower values, and that slows down all the mechanisms within the tumor dynamics equation. Then to describe the mechanic problem, and we assume that BPH and prostate cancer are slow processes, which according to the literature is true. BPH can take several years to develop, and prostate cancer is a slow-growing tumor. So that qualifies for using quasi-static linear elasticity, which is a normal assumption in mathematical oncology. And then because of a similar reason, we also use linear elasticity to describe the deformation of the tissue and the tumor. And to represent the forces exerted by both prostate cancer and BPH, we use pressure-like terms in the constitutive equation of the stress tensor. For prostate cancer, we use a linear term depending on the phase field. And for BPH, we use an increasing term that is only defined on the central gland, which is the only part of the prostate that can exhibit BPH. Now, we use the same numerical methods as before, and we complete the mechanic problem with Winkler-type boundary conditions to represent the reaction of nearby tissues and organs to the growth of the prostate due to prostate cancer and BPH. So as the prostate grows in size due to these pathologies, the boundary condition increases with an opposed reaction to constrain the growth. And the only exception is along the urethra, where we have free displacement. So using this model, we wanted to do two simulations. One where we didn't take into account the effect of BPH prior to the diagnosis of prostate cancer, and another one in which we took into account the development of mechanical stress due to BPH before the onset of prostate cancer. So that means that while we can get parameters from the literature for the main model, as we did for the previous study that I explained, and also for some of the parameters representing tumor growth based on other studies on mechanically constrained solid tumor growth, we still needed to characterize the rate of BPH, the Winkler boundary condition constant, and get an estimate of the pre-stress existing in the prostate before prostate cancer starts. So for this study, we did an inverse problem in which what we wanted to do is to run backwards the mechanic problem only using the BPH term. And we wanted to deform the current geometry of the patient's prostate as observed in an MRI image back to geometry that would match a healthy prostate according to anatomic atlases like Gray's Anatomy or Gynecology Urology. And in doing that, we would retrieve an estimate of these two parameters and also automatically as a byproduct, the press stress due to BPH before prostate cancer starts. So as I anticipated, for this study, we use data from one patient from this data set here, which is published. And it corresponded to a 54-year-old man who had 52 or almost 53 cubic centimeters volume of the prostate and a central line of 33 cubic centimeters, which I am representing here. So now we run our two simulations. On the left, you're seeing one in which we do not take into account the press stress due to BPH for the patient. And on the right, you see the same simulation, but including this press stress due to BPH before the detection of prostate cancer. You can see that there is a dramatic difference. And that comes from the effect of mechanical stress on tumor dynamics. So you can see that in this case on the left, we see that the tumor branches out in order to invade the prostatic tissue, whereas in this other one here, even though there is some growth, it is much more slowly over the same period of time. And because of this, we concluded that BPH can slow growth rate, induce minimal invasiveness in the tumor, avoid branching, and maintain the tumor at a small volume. And this observation can have a huge clinical impact. First of all, we would recommend reduction of the BPH treatments aiming at reducing the prostate volume, because the moment you reduce prostate volume in this situation, you would release the mechanical constraint on the tumor, and that would favor tumor growth. Then, these results also suggest that it would be possible to develop new BPH treatments maintaining a significant stress level in the organ to control tumor growth. And also, we could combine these models with longitudinal data in order to predict the development of BPH and prostate cancer, and then decide how to treat each of those diseases. So we wanted to pursue this last line of work, and we found ourselves with a problem, which is that these models that I have presented so far have between 12 and 16 parameters. And we don't have that much data for each patient in active surveillance. Usually, we can get 2 or 3 images for the patient, and between 3 to 7 PSA data. But this means, even though this looks like a lot of data, it only helps you parameterize a subset of the parameters that you need in the model. So because we wanted to switch gears and go to something that is more practical, we reset our minds modeling-wise. And we wanted to go to the simplest model that we can think of, but that could be practically implemented in the clinic. So we want a simple model that describes key mechanisms of prostate cancer growth, and we're going to focus just on the two. We're going to forget about PSA for the last part of this talk. And we want the model to represent key clinical variables. So to do that, we resorted to probably the most used model in mathematical oncology to represent solid tumor growth in 3D, which is the Fisher-Hall model of evacuation, also known simply as a reaction diffusion model in mathematical oncology community. And in this model, we only have 2 mechanisms. We have a diffusion process that tries to expand the tumor in size. And we have a logistic proliferation term that takes together all the proliferation and death processes that happens in the tumor. And this process here tries to increase the tumor cell density in the tumor. So our main variable here is no longer the phase field, but rather the tumor cell density N. And as before, we want to focus on tumors that grow inside of the prostate. So for this equation, for this model, we use zero flux boundary conditions. Now, from this model, we can easily calculate, as before, first, a 3D map of what the tumor looks like over time. And then from this map, we can calculate the tumor volume and the total tumor cell volume. And the difference between them is that the tumor volume is just a volumetric integral over the tumor region, whereas the total tumor cell volume is weighted with the local tumor cell density, normalized to theta, which is the carrying capacity or the maximal tumor cell density that is admissible at any point of the prostatic tissue. So how are we going to parameterize this model? Well, we're going to use 2 different types of magnetic resonance imaging data. The first one is T2-weighted maps, which, as you can see here, provide a lot of detail regarding the prostate and the nearby organs. Here you can see the prostate in the middle. Here you have 2 muscles on the 2 sides, and this is the rectum. These images are taken in an axial plane. That means a plane that is orthogonal to the vertebral column. But because we get a stack of images, we can also represent what happens in the coronal plane, that is a plane that divides the body in front and back, and also in the sagittal plane that divides up the body in left and right. So because we have a lot of anatomical detail, we can represent the prostate in red, the central gland in blue, and the tumor in yellow. But for prostate cancer, there is another type of magnetic resonance imaging that is also made in a standard way during the monitoring and diagnosis of the tumor. And that's diffusion-weighted MRI, from which we can take a variable called the apparent diffusion coefficient, which is an estimate of the free movement of water in the tissue. So the higher the ADC, the lower the tumor cell density, because the lower the cell density, because the water can move freely between the cells. And the lower the ADC, the higher the cellularity, and we take this property to define where the tumor is. If you look at this axial section of the prostate here, you can see that there is a dark spot over this area that actually characterizes the tumor in this imaging sequence. You can also see it in the coronal and in the sagittal plane. So what we do is we define the volumes of the prostate and the tumor using T2-weighted data. We then refine the volume of the tumor using apparent diffusion coefficient, and then we restrain the ADC map to within the tumor volume to define 3D map of tumor cell density using this formula that you see here that was developed upon many different studies on imaging of solid tumors and mathematical modeling of solid tumor growth. And what it simply introduces a linear dependency between the ADC that we obtain from imaging and the tumor cell density that we need to parameterize our model. And this dependency depends on two metrics that we need to take from the data and from cohort data. The ADCH, which is an estimate of ADC or apparent diffusion coefficient in the healthy tissue. For instance, for this patient, we could take volume of healthy tissue equal to the tumor volume in this part of the prostate that I'm pointing out here. And then we average the ADC values. That would be a good estimate for ADCH. And ADC minimum, that would be the minimum ADC that a prostatic tumor could have. And we took that from longitudinal studies over large patient cohorts in the literature. So at this point, we can define the prostate volume, the tumor volume, and the internal tumor cell density map within the tumor for each patient at each imaging time point. But as I mentioned before, we have longitudinal imaging. That means that we have images at different time points, and what happens is that they are collected in different physical coordinates, and the prostate may change its orientation in each of the imaging time points. So they can be in different places when you load them up together. And to correct for this, what we need to do is a registration, which is a mapping that takes the prostate segmentations and map them all together to a reference geometry of the prostate. In our case, we use an unrigid algorithm that is a deformable algorithm that aligns the prostate segmentations from the second and the third time point to the first time point that we have for each patient. That is, for the time point used for diagnosis. After we have segmented and registered our data, we have all the imaging and segmentations together in the same prostate geometry. We can now assess the evolution of the tumor over time. So at this point, we make an anatomic model consisting of an isogeometric mesh for the prostate, where we also project the tumor cell density that we got from ADC maps. Then we convert ADC to tumor cell density, as I showed before. Then we run a calibration problem to determine the diffusivity of tumor cell density and the tumor cell net proliferation, which are the two parameters governing the mechanisms in the model. And finally, we can perform forecasting, which we can compare to further data if available for the patient. So just to provide an overview of what methods I'm using here, the meshing method is exactly the same as I was using before. The solvers are the same, but now I need a model calibration method. And we simply use the Gauss-Newton method. So what we do is we take the first imaging dataset and we use it for initialization of the model. Then we take a second dataset, and at least a second dataset, it can be more if we have more, but at least a second dataset which we use as a target for the calibration problem. And we said that we want to minimize the relative L2 error between the imaging measurement and the model prediction of the tumor cell density at the second time point. So that would be the function of this calibration problem. Now let me show you some results over a small patient cohort. In order to test the applicability of our model and methods, we collaborated with Dr. Michaelis at the UT Health Science Center at San Antonio, where they have been developing a lot of imaging techniques and clinical protocols for prostate cancer. And he gave us 7 patients that have 7 patient data sets, not 7 human patients, who have 3 longitudinal NP-MRI scans with a visible tumor in the 3 scans that was confirmed through biopsy at least once. Then we started analyzing this data, and we observed that these patients have been in active surveillance for a median of 3.5 years, some of them up to almost 5 years. And the inter-scan times were more or less a year and a half. So we have patients that are in this clinical protocol called active surveillance for a very long time. And this speaks again about the applicability of a model that can predict whether the patient or not, whether the patient can stay or not in this clinical protocol, because the timing between these scans can be up to almost 3 years. So in those 3 years, the tumor can completely change or can stay almost in a quiescent state, and you need to tell the difference between those in order to recommend patient-specific advice to each individual patient in active surveillance. So we took this data and we thought, well, we can do 2 studies here. We can take all the data and we can try to calibrate the model using all the data. And the objective of this study would be to test whether the model can recapitulate tumor growth over active surveillance. And then we can also do a fitting forecasting study where we initialize the model with the first scan, we calibrate with the second one, and then we take a forecast up to the 3rd scan time point, and we compare the model prediction with the data at that time. And for the global calibration studies, we were amazed to see that the model was able to reproduce the total volume and the range of values of tumor cell density over the tumor. Here I'm showing results for 4 representative patients in the cohort, and you can see that while globally the tumor predicted by the model, which is the one on the right for each of the 4 patients, the tumor measured from imaging data at the 2nd and 3rd time points, they look alike qualitatively at a global point, but when you start looking locally, you see that the shape and the heterogeneity of the tumor cell density map is still very limited, which is normal because the model that we are using here, recall that it was very simple, and we just wanted to test the applicability on a clinical scenario, on a practical clinical scenario. So in order to have a better understanding of how well we are performing, we analyze these results at the global and the local level. At the global level, we use the 2 markers that I mentioned before, the tumor volume and the total tumor cell volume. And we do a unity test in which we plot the corresponding metric measured over the data in the horizontal axis and the quantity predicted by the model on the vertical axis. And then we can calculate Pearson and concordance correlation coefficients. And we observe that we're getting values over 0.97 for both of them. So at a global scale, the model is performing well. The problem comes when we start going locally. So here we took 4 different local metrics. The first one is the Dice coefficient, which assesses the agreement in the shape of the tumor measured over the imaging data and the tumor predicted by the model. We're getting values that are on average around 0.8. More or less, that's the value where most neural networks operate when you want to automatically segment a tumor. So we think that these results are promising, but we want to be over 0.8 for all patients. And here we have some patients for which we need to improve that prediction. And then the other 3 metrics are the root mean squared error, the Pearson concordance correlation, and the Pearson correlation coefficient and the concordance correlation coefficient, which measure the agreement between the 3D tumor cell density map obtained from ADC from the imaging data and the tumor cell density map predicted by the model. And while the RMSE is quite low, it's below 0.1, we see that we would like to improve the PCC and the CCC values. Usually, most solid tumor growth models used for tumor forecasting operate between 0.5 and 0.8. And here, even when the model is quite simple, we are in between 0.3 and 0.6, I would say, for the majority of the patients. So we think we're at a promising first step towards developing a practical model for prostate cancer. And we didn't observe significant differences in between the recapitulation of the tumors at the 2nd and 3rd time points, which are represented in blue and green in this plot. But when we do this contrast at a patient-specific manner, we do see that the predictions, or well, the recapitulation at the 3rd time point is slightly worse in the 3rd time point according to Wilcoxon cycle tests. But now the big question is, okay, so we can recapitulate tumor growth at the global scale, we can do better at local scale, but what happens when we do a fitting forecasting study? Because that's what we would like to pass to the physicians working in active surveillance. Well, we were happy to observe that the performance is pretty much the same. If you don't trust me, here is the proof. I mean, here you can see on the left the global calibration results, and on the right the fitting forecasting results. So at the global level, they perform equally well, and at the local level, we see the same limitation. We would like to better represent the changes in shape and the changes in the heterogeneity of tumor cell density within the tumor. Again, if we analyze the global metrics as before, we again obtain Pearson and concordance correlation coefficients in the order of 0.90 more or less and over. And when we go locally, we observe the same results as before. So when we try to do a prediction, we observe a relatively worse performance that is not significant when we compare the results over the whole cohort, but it becomes significant when we compare on a patient-wide scenario using a paired Wilkinson cycle test. So now we said, okay, is there any difference between the global calibration and the fitting forecasting study? And well, we compare the results, and there are no significant differences at all. But there is still a big question here, which is, okay, we can recapitulate the volume of the tumor and the total tumor cell volume. That's informative for patients, for physicians, but they wanted to know whether or not the tumor is going to evolve towards a higher risk state. So we needed to have some kind of metric that would help us look at this data and obtain that probability of progression to higher risk disease. So towards that end, we wanted to build a high-rate disease risk classifier. So we wanted to use a data-driven algorithm that would take the forecasts and provide a probability of progression towards high-risk disease. Towards that end, because the prostate cancer risk is deeply rooted on the histopathology, we took all the measurements of histopathology for these patients, which were a total of 16 measurements across the 7 patients, and we divided them into lower risk prostate cancer and higher risk prostate cancer, because depending on the clinical guideline of active surveillance, any presence of what's called Gleason grade 4 represents higher risk disease. And also because this way we have a balanced data set in our study. And what we did is at the same times that these histopathological measurements were made, we used our model results for the global calibration study to calculate 6 potential markers of high risk disease. The first 3 are the prostate volume, the tumor volume, and the total tumor cell volume. And then the other 3 are ones that we defined for our study. The first one is the mean tumor cell density averaged over the tumor volume. The next one is the total tumor cell index, which is the product of the mean tumor cell density times the tumor volume divided by the volume of the prostate. And this new metric here aims at taking into account the direct relationship that the mean tumor cell density and the tumor volume have with progression to higher risk disease, and the inverse relationship that exists between the higher prostate volume and the lower risk of higher risk disease, as I mentioned before. And then the last metric that we use is the mean tumor proliferation, which is just the integration over the prostate, the integration over the tumor of the logistic term of our model averaged to the volume of the tumor. So calculating these markers over the 2 groups of tumors, the lower Gleason score tumors or lower risk tumors and the higher risk tumors, we only observe significant differences for the mean tumor proliferation. But we see a positive trend towards higher total tumor cell index for the total tumor cell index in the higher risk group. So we said, okay, now we can use this marker and potentially the combination of these 2 markers in order to train a classifier to distinguish between high risk and lower risk disease. And to do that, we use a logistic classifier. So in a nutshell, what we have is data about the markers that come from the mathematical model forecasts, and also the class of the tumor to train the classifier, which would be either low risk, which would be probabilities close to 0, and higher risk prostate cancer, which would be probabilities of higher risk closer to 1. We train this classifier, that is, we calculate the coefficients that appear here using the maximum likelihood method over the whole patient cohort. And then we do receiver operating characteristic curve analysis, which if you're not familiar with it, what we do here is after the classifier is trained, the actual probabilities for each of the tumor measurements can be close to 0 or up to 1. But we can take different thresholds of this probability to set the threshold for what we consider as a high-risk prostate cancer. As you move up towards 1, you are making a lot of mistakes classifying tumors because you are essentially classifying everything as a tumor and you're missing the low-risk cases. And if you're too close to 0, then you mean that you're saying that almost everything is low-risk disease, so you are missing the high-risk cases. So you want to calculate two metrics here, the sensitivity and the specificity. For each threshold that you set to define high-risk disease, you calculate the sensitivity as the number of correctly classified high-risk cases over the total number of high-risk cases, and then you calculate the specificity as the total number of correctly classified low-risk cases divided over the total number of low-risk cases. If you plot then sensitivity with respect to 1 minus specificity, you obtain the so-called ROC curve, which is used to assess the performance of the classifier in separating low risk from high risk prostate cancer in our problem. And the closest the curve is towards the left upper corner, the better your classifier is. And the usual method to assess that is the area under the curve. And usually you want an AUC, or area under the curve, over 0.75. And as you can see here, for this simple implementation, when we only use the average tumor proliferation, we get 0.77. And when we combine this metric with this other one, we obtain 0.83. But the optimal performance point, which is the point of the curve closest to this optimal product here, operates at optimal sensitivity to specificity of 75%, which more or less matches the usual performance of the classifiers that are only based on imaging data for prostate cancer and other solid tumors. And so it's a good starting point to keep developing these classifier techniques. Now, importantly, as we can obtain the dynamics of the markers from our dynamic forecasts of tumor growth, we can also obtain trajectories of the classifier over time that can help us predict whether the tumor is going to progress to higher risk disease. And that's what we are showing here. But in the interest of time, I'm going to focus on one patient only. So here, in this on the left, I'm showing the results from the PT forecasting study for a patient that has a growing tumor that also progressed from a Gleason 3+3, which is low risk, to Gleason 3+4, which is intermediate risk. And what we observe here is the trajectory of the classifier coming from the forecast of the model following calibration. The solid line corresponds to the calibration time span, and the dashed line corresponds to the forecast after the second imaging time point. And what we observe here is that by informing the model with the data up to the second imaging time point, we can anticipate progression towards higher risk 1,000 days before. That is approximately 2.5 years. So that would give enough time to anticipate an imaging scan before the actual third MRI scan was performed and start planning a therapy or a surgery for this patient way before it was performed. So this is the kind of technologies that combines mathematical modeling and data-driven algorithms that we are interested in right now, and that we are keeping developing in collaboration with UT San Antonio and the MD Anderson Cancer Center in Houston. So to conclude, I would say that active surveillance of prostate cancer is an ideal setting to benefit from mathematical modeling to guide personalized clinical decision making, as I've shown in the results that I presented today. As you could see, our models show promise reproducing and predicting prostate cancer growth as observed in clinical practice, and high-risk disease diagnosis should account for tumor dynamics. We cannot only rely on the observations that we are doing right now. We also need to take into account how the tumor is going to change after the last monitoring exam was performed in order to decide what's the best management option for each individual patient. And as I was mentioning, we are collaborating with UT San Antonio and MD Anderson to get further data in order to test and develop our models over a larger cohort. We want to extend the practical model that I presented today in the last part to include mechanics and PSA dynamics as the first two models that I presented. We also want to assess the added value of these two mechanisms on top of the model that I presented today in order to assess whether there is further information that we can get from there and how can we use that information. For instance, we anticipate that because PSA tests are performed more often, we can get dynamic information of the tumor proliferation from there. And then for mechanics, because it's a 3D resolved mechanism, we can improve the heterogeneity of our predictions by accounting by the local mechanical stress within the tumor and around the tumor. And finally, we also want to extend our models to incorporate treatment response, for instance, radiotherapy. I have not presented it today, but I have done some work also on modeling the response to radiotherapy and the optimal control of the tumor using chemotherapy and a type of targeted therapy called anti-androgenic therapy, which tries to reduce the vascularity that supports the tumor and therefore ends up reducing tumor growth. But because there is a lot of prostatic tumors that can benefit from active surveillance, we want to focus on this open problem that the urologic community has and help them develop predictive markers that account for tumor dynamics in order to decide what's the best option for each individual patient. Finally, I would like to introduce you to the core team that has been working on this problem with me, which includes my PhD advisor, Dr. Gómez, which was in the University of A Coruña, but now is at Purdue University, and my postdoc advisors, Alessandro Reali from the University of Pavia, Tom Hughes and Tom Yankila from the Austin. I also have enjoyed a lot of collaborations with people both in Europe and in the US, and I also would like to thank the supercomputing centers that have contributed to the result that I presented today, and the funding that I received over the years has supported my research, and I hope keep supporting my research in the future. I also have to disclose that even though I presented myself as a researcher from the University of Pavia and the Austin, truth is that last Friday I moved back to Spain, and I'm now at Santiago de Compostela. So these results were mostly done during my time at Pavia and Austin, and I will keep my collaboration with UT Austin to keep enjoying the collaboration on modeling and also access to patient data with them. So with that, I would like to finish my talk, and thank you for staying here until the end. And if you have any questions now, I'm happy to address them.
Thank you for your talk. Are there some questions?
So, excuse me for my question, because I'm not a specialist in such things, although I'm a bit interested in topological data analysis, but my question is practical. So we have a group of people in our university who work on, say, predicting the results, the outcome of chemotherapy of various cancer disease and so on. So they told me that for them, the biggest problem is that if they mathematically, from their mathematical models, it appears that you have changed some practice. It's not possible because there are strict medical procedures, and you cannot somehow recommend somebody to make some new therapy which is not in accordance with this practice. So in your case, what can you do?
Yes, that's a very good question, and the bone of my, well, the main issue that we face when we collaborate with physicians. I'm going to respond in two steps. The first one, regarding my work, there is not a biggest struggle from the physicians working on active surveillance, because in active surveillance, you just need to decide the frequency of testing. So they are quite open at doing more frequent imaging scans or more frequent PSA tests, as long as you are within the framework of what active surveillance is accepted all over the world. And that means doing imaging between 1 and 3 years apart, PSA tests between 3 and 12 months apart. And our models so far recommend that. So we are within their accepted clinical framework. Now, therapy is another thing. As you were saying, if you want to change therapy, you have to abide by the accepted therapies that exist in the clinic right now. And that means that you have to control not only the total dosage, but also the frequency of those dosages. And if you want to change either of these two things, you need to be inside of the clinically accepted protocols, and they are very, very, very strict. So the majority of mathematical models, for instance, using optimal control problems or directly optimizing treatment, recommend either dosages or frequencies for the dosages that are outside what's clinically acceptable. So what we have seen in the last years in computational oncology is that those therapies are being tested either in silico, using the results of the model after parameterizing them with the standard of care for the patient, and then assessing what would have happened if you had used a different protocol. And what you get from that is that there are some patients that definitely benefit from a standard protocol, but there are other patients that can have a much better outcome from the protocols predicted by the models. And then, in order to have a more quantitative and real-world evaluation of these models, there are other studies that are performed on animals, like rats, mice, things like that. And they also show that you can improve radiotherapy and chemotherapy using the results of the model. But the problem is that when you want to scale this up to humans, you need to abide by what's called a clinical trial. And that involves different steps that go from assessing your model with animal or cellular data first, then doing a small study where you follow patients in parallel with your model. And when that's approved, then you can move on and do the golden standard in medicine right now, which is a double-blind randomized study, which means that you're going to take a board of patients and you're going to randomize them without either the physician or the patient knowing if the treatment is the standard one or the one that is predicted by the model. So the difficulty here is that if you get a very weird treatment, you're going to say, yeah, this comes from the model. And if you get something like that's more practical, you're going to say, yeah, this is the standard one. But let's say that that's a barrier that has been there for a long time. And over the last year, I think the steps that have been taken to improve the applicability of models in the clinic has been either monitoring patients or doing in silico tests to assess what-if scenarios. And because of those, right now there are some clinical trials that incorporate models to decide which standard treatment is best for each patient, or that aim at predicting whether or not the standard of care is going to be good, but without intervening in the patient. So it's an open problem, but I think that the recent developments in the field are taking us towards a better implementation of these models in the clinic. But the key step is making the models practical. That's why I started with more complicated models, and then I stepped down towards something simpler, but more practical, where we can get actual insights that can help physicians. I hope I responded to your question.
Great, thank you.
Are there some other question?
One more question, because in your work you needed somehow image processing as well. So when people working in topological data analysis, they always say that there are some imprecise things caused by, well, just by physical reasons. That the body can be in this position or that position. You cannot do it exactly. So what is it difficult in your model somehow to avoid this type of complications?
That's a very good question. And yes, I agree that when you do registration, you have to embrace certain approximations that you would like to avoid. And the reason for that is that you don't know what's the best way to match the prostate geometries over time. So what we usually do is follow what the imaging community do in order to do a registration for surgical purposes. What they want to do is to use a geometric reference for one of the patients, like I said, for instance, first scan. And then, because tumor growth is a progressive problem, you expect that the volume of the tumor is going to grow. So in order to avoid size reductions due to the registration algorithm, we use tumor preserving constraint in the objective function of the registration method. So with that, when you register everything together, you match the prostate geometries, which is what you want to see the evolution of the tumor, but you maintain the sizes of the tumor. Otherwise, if you don't have that term, sometimes if the changes of the volume of the prostate are large, you get an artificial reduction of the tumor at the latest dates. And you want to avoid that to properly characterize tumor. But that, again, it's based on the results of the imaging community. Actually, my colleagues in UT have been using these algorithms before for breast and brain cancer as well. We developed them for prostatic tumor as well, in collaboration actually with John Heiselman here and Michael Niga, who are experts on registration problems for imaging data for practical purposes.
Okay, then maybe you can do further questions personally to the speaker, and we can thank him again.